Bismillah ar-Rahman ar-Rahim. Welcome to Tahar Scholar. We are الأحد 24 September 23 or Sunday 24 September 23 in Malaysia. So this week we start our tutorials. This is the first series dedicated to the first chapter. So each chapter has a series, the root of an equation. Before to solve the exercises of the series, let's take first an overview of the series on the screen and then come back. So this is our first series number 1. Each chapter has a series of exercises. This is chapter 1, the root of an equation, the module numerical method, the channel Tahar Scholar, and the copyright of Tarjumat. So let's see a brief overview of the series, and then we go back to our setting with the notebook and the pen and solve the exercises. The first exercise is to solve a quadratic equation, both with Abou Kamel's method, numerically, and with analytical method, and try to compare the two methods. The second exercise is a list of equations, nonlinear equations, with their corresponding interval. We solve only one equation, namely the second equation, sin x minus x squared, and in detail with the table and calculator. And we give the results for the others. This is to practice the method. So the same method, whatever the complexity of the equation you have. And we will not exceed 5 iterations. And the third exercise is actually a physical model that modelize the fall of the parachutist. And from that model, we extract an equation, and then we solve it to solve our problem. So this shows how to use numerical method in the real world, albeit it's a simple model, of course, because in the real world you don't have a logarithm or sine, cosine, etc., x squared. You have a physical model, and then you use your skills in calculus, in physics, in algebra, and in numerical methods combined together, not numerical methods only. So it shows here the power of this method to solve a real world problem. So let's come back to our setting and solve the exercises in detail. Okay. So now let's solve exercise number 1. Quadratic equation. Now we chosen quadratic equation because we can solve it analytically, and then we can compare the exact solution with the approximative solution. Quadratic equation. We have two questions. The first, we solve the equation with Abou Kamel's method, and then we solve it with the analytical way, and we compare. Compare means we calculate the relative error, the exact relative error. So, as we have seen in the lecture, I think lecture number I think, number 3. We have 5 lectures. We have a lecture dedicated to solving an equation using a table and a calculator. We will repeat the method here. This is the goal of this tutorial, is to master this table, how to fit this table with the calculator. So let's first write our equation. 0, 4 x squared plus 2x plus 4.7 equals 0, with x must be in 5, 10, in the interval 5, 10. So this is our equation. And just below it, let's draw our table. So this is our table. We fill it first with the input data. We have the lower bound and the upper bound. And we said that the first iteration is always 100%. And then we fill the table. But before that, let's recall the rules, the 3 rules of the method. The first is the false point. The formula of the false point, very simple, Fu xl minus fl xu over Fu minus fl. And the second rule is the approximative relative error at the ith iteration is the current false point minus the previous false point over the current by 100%. We need that to assess the progress of the false points. And third is the rule of the signs. So if the sign of Fli, the image of the lower bound, is different from the sign of Fli, the image of the false point, they have different signs, then it is at the left. The next interval is at the left. Otherwise, at the right. So 3 simple rules to use while filling the table. We have our equation. We take 5 in the equation to get the image. So try to practice with me. You can, of course, pause the video, try to fill the first and the second, or pause the video at each cell, as you like. So 5, when we replace it here in the function, we get 5.7. This is the function. So we get 5.7. For 10, we get minus 13.3. And then we use the formula of XR. For sake of pedagogy, to note down what we do as calculation, we will write it here. We write it here down. So iteration, but for the other tables, we will directly work directly on the table. So iteration number 1. So we do that only, we go slowly only for this table for pedagogical reason. So iteration number 1, first thing, we have seen FL number 1 is the image of XL number 1. And we have found it's 5.7. And we did also the same for FU, for the first iteration. It's the image of XU1, and we found minus 13.3. And you can observe that they have different sign. If they have both the same sign, positive, positive, or negative, negative, it's impossible the interval contains the solution. We have made an error in the interval. So we can check the function is continuous, of course, and it changed its sign at the endpoints. So let's note that different FL1 and FU1 have different signs. This is important. Then let's apply the formula of XR1. So we have FU and FL in the numerator and the denominator. So let's write it here, minus 13.3, leave space for the x's, and 5.7, both in the numerator and the denominator. And then the x is 5, 10, 5, and 10. And with the calculator, we find the value. Try to do that with me, please. 6.5. This is XR1. Then the image, FR1, is the image of XR1. And we take the value 6.5 and we replace it here. This is fx. This is fx. And we obtain 2.1. And we report the values in the table. So we have 6.5. This column with green is with Abou Kamel, formula. And this is the most important column. And then the value 0.1. And as I said, the error always is 100% at the first iteration, so that in the table at least you have to do at least two rows, 2 iterations. Before to go to the second iteration, we need to apply the sign rule, the rule of the signs. So we check FR, sign of FR, and the sign of FL. And we can see that they are both positive. So it is impossible that the curve cuts the x-axis at the left. So it's at the right. Now let's write it here. The sign of the rule, sign of FL1 is equal to the sign of FL1. And this implies that the next interval is at the right. We have seen in the lecture, in the example, I think section 1.3, I think, section 1. We have seen the problem, the method, and then the application. So it's section 1.3, we have seen there the next interval is always at the left. In this exercise, the interval is always at the right. So at the right means that the next interval, xl2, the lower bound of the interval, and the upper bound of the interval of the next iteration, the upper will not change. So the same as the current. But the lower bound will take the value of xl1. So I explain here in detail in order to understand the method. But once you are familiar to the method, you will fill directly the table. You don't have to write all this. We will do that in the second exercise. So here we will go slowly, particularly for those who have not yet grasped the method. So what we do, XR will change. So we take these two values, XR and FR, and we put them here at the lower bound and its image, while the upper bound will not change. It's the same, 10 and minus 30. And here we write 6.5 and 2.1. We check when we copy. Be careful, because if you do a mistake, all the rest is wrong. 6.5, 2.1. So we have the 4 cells without any calculation, just applying the rule of the signs of FR and FL. Then iteration number 2, we apply the Abou Kamel method, the rule of the Abou Kamel method. So iteration number 2, XR number 2, FU and FL. FU is minus 13.3 and FL is now 2.1. So let's write it here, 3.3 minus 2.1 over same 2.1. And for the x's is not 5, is 6.5 and 10. Is 6.5 and 10. And with the calculator, you can try with me. You can pause, of course, problem, and we'll find 6,977. I always in exercises work with 3 decimal digits, because more than that, we will lose precision. Of course, we lose a little bit of precision due to the round-off errors. But it will be really hard to write down 5, 6, 7 digits. So 977. We take this image, we take this abscissor XR, and we calculate its image. So by definition, it's the image of XR. Take that here, calculate, and you will find the value 0.578. So let us report this to value, XR and its image of the current iteration, 6,977 and 0.578. And you can observe that XR is always bracketed between 5 and 10. If you find here, for example, 11 or 3 or 2.5, don't continue, you have made a mistake. And FR in its absolute value should also decrease. Now let's calculate the error to assess the progress. So this is first point. Second point is the error at the second iteration. It is the current minus the previous over the current, but times 100%. So 6,977 minus 6.5 over 6,977 by times 100%. And we get the value 6.8. Here I use only one decimal now because I don't need much precision here. Just an average to know if I have to continue or break the table. The iteration, I mean. 6.8%. So I report that here, 6.8%. The error is still big. We have to, as the exercise tells us, we have to stop when the error is less than 1%, or we have reached the fifth iteration. So 6.8%, we apply this, the rule of the signs in order to go to the third iteration. Same, the sign of FR and FL, they have the same sign, so we stay at the right. And I said in the lectures that one feature of this method is generally, like 90% of the cases, it does not oscillate. So if it catches the solution, the root at the right, it will keep in the subsequent iterations at the right. So let's check it again here, sign. Let's write it here. FL of the second iteration is the same, has the same sign as FR of the second iteration, which means still at the right. And means for the, because the interval is defined by its endpoints, XR2, XR3, I mean, the next interval, and XU3. At the right means the upper will not change, so it is equal to the current upper bound, but the lower bound will take the current value of XR. And let's report that. Let's apply this in the table, so this will not change. XU and its image, and we take XR and its image and we put them here in these two cells. So 6977 and 0578. I check it again. Okay, and then we can apply the Abou Kamel's formula. We need these four cells. So for the other iterations, we will not repeat the same points. We only report XR. Because the formula, it's better to write it down and not do that in your brain mentally. So iteration, for the other iterations, that is the third and the fourth and the fifth, we write down only XR, the false point. So XR third iteration is FU, FL. FU is minus 13.3 minus 0.578 in the numerator and the denominator. And for the x's, it's 6977, 6977, and 10. 10 will not change, the same. And with the calculator, we find the value 7.103, 7.103. And we calculate its image, report it here, 7.103. Take this value in the function, and we get the image with the calculator. We have the function, so we don't have to write it down. We have the function. We replace, and we get the value 0, 1, 4, 6. So again, the XR is bracketed and FR is decreasing, is tending to 0. Let's do now the error. The error, also we don't have to write it down, it's very simple. This value, the current, minus the previous over the current. 7,103 minus 6.977 over 7.103 times 100. And you'll find with the calculator, it's very easy, you'll find the value, check with me, 1.8%. And again, the rule of the signs, you have the rules here, the rule of the signs, the right and the left. No multiplication, just see the signs. They are both positive, so we are still at the right. If you find the interval has changed its position at the left, it was at the right, and then be suspicious, because in general it does not oscillate, as I have said it again and again. So let's apply. Here we have to, so at the right, we take the two value here, XR and its image. And here better don't do mentally, but write the formula. So XR4, the fourth iteration, is FU and FL minus 13.3, leave space here, and FL is 0,146, both at the numerator and the denominator. And then for XL, 7,103 and XU. And then, so I have written all the terms of the formula, and now I can use my calculator and find the result. And I found 7,134. I report it in the table. And then I take the value of XR in the function to get its image, and I obtain 0.037. So it decreases and it's bracketed. And then we check the progress, the error, this value minus the current value of XR minus the previous over the current by times 100%. And I find 0.4%. Well, the error, the absolute value of the error is less than 1%. So I stop. I don't have to continue, because in the exercise I asked to stop when the error is less than 1%. It's precision enough with the calculator. With the program, of course, you can continue as long as you want, 1%, 0.1%, 0.001%, etc. So our solution with this error is this one. So let's write it here. I have still space. Let's write the conclusion here. Conclusion here. Our solution at the fourth iteration is XR 7134 with an error of 0.4%. of 0.4%. And you can see that FR is still far from being zero. It's a 0, 0. But this is the asked precision. If we do that, as I said, with a calculator, it will take several, I think, eight or nine iterations to reach a good precision. So that's it for the first part of the exercise. First part, we solved the problem using Abou Kamel's method. Let's do now the analytical method. So now let's solve our equation with the analytical method, which is very easy, of course. Delta discriminant b square minus 4ac, with here a equal minus 0.4, b is 2.2, and c the coefficients of the polynomial 4.7. And we replace the value. So we have 2.2 square minus 4 minus 0.4 by 4.7. And with the calculator, we find 12,360. Positive means we have two solutions. So we have two solutions, x1 and 2 equal minus b plus minus delta, square root of delta over 2a. And we find with the calculator, the first with plus, find minus 1,645. And with plus, we find 7,145. So our solution is close to this root. The equation has actually two roots, but because we have chosen the interval 5, 10, we got the exact root in this interval. And we can calculate the exact relative error. Exact relative error by definition is XR that we have found with the Abou Kamel method at the fourth iteration. So this is at the fourth iteration minus XR star, the exact solution that we have found analytically, over XR4. So it's relative to the fourth point with 100%. And we find minus 0.15%. So it's really close to the exact solution. We have an error less than 1 in its absolute value, less than 1%. This is the exact. In general, we cannot calculate the exact error, relative error, because we don't know the exact solution. But in this case, a simple case, we can apply an analytical method, the analytical method, and we can compare. So the exact relative error. So let's come back to we have two roots. Let's draw. This is just a note. It's not asked in. It's not a task in our exercise, but just to observe the equation. Quadratic, it generally is a parabola. So this is the origin, and the curve should be like this. Approximately, of course, has an axis of symmetry somewhere here. And tangent here, parallel to the x-axis. So it cuts here between 5 and 10. This is the second root, exact root, 7, 1, 4, 5. And because we have worked with this interval, we got a solution close to the exact, the second exact solution, x2. You can repeat the same table. You can repeat as exercise. You can repeat the same method. It's always the same method, but in the interval 0, no, -5, 0, in this interval. And see if do exactly the same thing with Abou Kamel method and compare with the exact solution, calculate the exact relative error, and see if you are close to this second solution, to x1, -1, 6, 4, 5. So try to do that in the interval -5, 0. As we said in the lectures, this method can catch only one solution. We have taken this interval, we got a solution close to this exact solution. Try to do the same work, the same method as an exercise to practice the method, but with -5, 0. And you have already the exact solution, the two roots, the two exact roots. So that's it for exercise number 1.